Hi, I'm George Diath from the University of Exeter, and today I'll be talking about our work in Bayesian Optimisation. This was carried out with Richard Everson and Jonathan Fieldsend. In this talk, we'll be focusing on the problem of globally optimizing black box functions. These are defined on a compact domain, typically with box constraints. The functional form of f is not known and assumed to be non-convex, so we're unable to exploit any prior knowledge about the function, such as its derivative information. We're particularly interested in cases where these evaluations are expensive, in the sense that we're limited in the number of evaluations that may be performed, typically to a few hundred or lower. Bayesian optimization is a popular method for optimizing these black box functions. It consists of two main components. The first is a probabilistic surrogate model, parameterized by theta, which is usually a Gaussian process. It models the objective function by using previously evaluated locations and provides uncertainty estimates about any predictions made. The second is an acquisition function. These are cheap to query and leverage the surrogate model to guide the search by balancing the exploitation of locations with a good predictive value with the exploration of locations that have high amounts of uncertainty. We start by generating some data using a space-filling design, such as Latin hypercube sampling. Here, x is the decision vector and y is the measure response from the function f. The surrogate model is then fitted or trained. This is usually carried out by a maximum a posteriori estimate by maximising the marginal likelihood, also known as the model evidence. This is multiplied by the prior probability of the hyperparameters. Often, all hyperparameter values are assumed equally likely, and so this becomes the maximum likelihood estimate. Finally, the acquisition function is maximised to select the next location to expensively evaluate. Acquisition functions are based on the predictive distribution of the surrogate model and try to strike a balance between exploitation and exploration. The upper plot shows a surrogate model that has been trained on 3 locations in black, with predicted mean value in dark green and uncertainty in the shaded green region. The lower plot shows 2 different acquisition functions, expected improvement and upper confidence bound in red and blue respectively, and their maximisers are the dashed lines and circles. The EI acquisition function, as its name suggests, is the amount of expected improvement over the best seen value so far, f star. It is by far the most popular acquisition function, but has the tendency to overexploit in many situations. Several ad hoc approaches have been proposed to boost the exploration of EI, such as subtracting an amount from the best seen value. However, choosing this amount to subtract is far from trivial. The UCB acquisition function is an optimistic policy, that is the weighted sum of the predicted value of the model mu and the predicted standard deviation square root of v. The weight beta, however, is difficult to set correctly, and in practice we often set this heuristically. In the statistics community, using a fully Bayesian approach for modelling with GPs is fairly standard. However, in Bayesian optimization, which fits these GP surrogate models at each iteration, it is almost exclusively carried out with map estimates of the model's hyperparameters. This is problematic for a number of reasons, but primarily because we're not taking into account the uncertainty in the model's hyperparameters. If we wish to perform a fully Bayesian treatment of the GP hyperparameters in Bayesian optimization, we must use the integrated acquisition function. This is the standard acquisition function multiplied by the posterior probability of the evaluated hyperparameters, integrated over all possible hyperparameters. However, this is intractable, but we can approximate this integral using Monte Carlo integration, using samples drawn from the hyperparameter posterior. In doing so, we're taking into account the uncertainty in the hyperparameters themselves. Here is an example. The upper plot shows expected improvement for several GP models created using different posterior hyperparameter samples, with each maximum shown as the circles. Note how each hyperparameter sample would have resulted in a different location being selected to evaluate next. The lower plot shows the average of these, the integrated acquisition function. Before showing how we can do this practically, we'll first review Gaussian processes. When performing regression, we are often only able to observe noisy realizations y of some underlying function values f. These have normally been corrupted by Gaussian distributed noise, giving us the following observation model. In GP regression, we place a multivariate Gaussian prior over the latent variables f. The Gaussian has a kernel, or a covariance matrix K, which I'll talk about in the next slide, and a mean function for which, for ease of exposition, we'll define to be 0. However, other choices of mean function are seldom used. Because GPs are prior distributions of functions, such that any finite number of function values are distributed as a multivariate Gaussian, we can draw functions from the prior. These are shown as the different coloured lines here. Covariance functions encode our beliefs about the characteristics of the class of functions we wish to model, such as its smoothness. Those used in GP regression are typically stationary, meaning that they're just a function of the distance between 2 locations. In this work, we use the Matern 5.2 kernel, which is known to work better than the popular squared exponential kernel for less smooth functions. Here we show the isotropic version, in which there's only one length scale for all dimensions of the data. The length scale L controls how quickly correlation between location decays as a function of distance. The other hyperparameter here is sigma O. This is the output scale and controls the overall magnitude of the response. The ARD version of the kernel has a separate length scale for each dimension of the feature space, with the idea being that irrelevant dimensions will end up having large length scales and will thus be effectively ignored in the model. Equipped with some data at locations x and observed values y, a covariance function, and a likelihood model, we can make some predictions with our Gaussian process. The joint distribution between the GP prior and test locations is also a GP. Similarly, and more usefully, conditioning this joint distribution on the observations results in a GP with mean mu and variance v. Here we can see an example of a GP prior distribution on the left. Conditioning it on the observed values effectively removes all functions from the prior that do not agree with the data, leaving only function draws that go through the data points if there are no observation noise in this case. The hyperparameters of a GP are the likelihood noise term, the output scale of the kernel, and a single length scale for the isotropic kernel, or multiple length scales for an ARD kernel. A useful property of a GP is that we can calculate the marginal likelihood, also known as the model evidence of the data, for given hyperparameters. The logged version of this is typically used for numerical stability. It consists of three terms. The first is a data fit term, which promotes the model accurately predicting the training data, a complexity term which penalizes overly complex models, and a normalization constant to make it a distribution. Normally, the parameters that maximize the marginal log likelihood are chosen to make predictions with. This is often carried out via gradient descent optimization because, in calculating the marginal likelihood, the computation expensive parts of the gradient calculation have already been computed. The GP posterior distribution makes predictions assuming that the given parameters are correct. It does not take into account the fact that there's uncertainty in the parameter values themselves and is necessarily overconfident. Additionally, the landscape of the marginal likelihood is non-trivial to optimize and may require multiple restarts to optimize correctly. The landscape is likely to have multiple local maxima as well as large flat plateaus. In this figure, we can see 9 gradient-based optimization runs on a GP log marginal likelihood. Each run starts at one of the white circles, with the paths taken shown as the red dashed lines and their ending positions as the red circles. Many of the runs have got stuck on plateaus and only 2 runs have gotten close to the global optimum. It is worth noting that this is just a toy problem with one parameter fixed, and in the ARD kernel case then there will be 2 plus the problem dimensionality number of hyperparameters to optimize, which will be a much harder problem. A fully Bayesian approach with respect to the hyperparameters lets us take into account their uncertainty in the model predictions and thus optimization. The posterior predictive distribution of the fully Bayesian GP is an integral over all possible hyperparameters. It contains 2 terms. The left-hand term is the normal GP, which we can evaluate in closed form, but the right-hand side is the hyperparameter posterior, which is intractable. Again, we can approximate this distribution with Monte Carlo integration. Therefore, we need to turn to approximate inference methods in order to draw the samples needed for this approximation. Approximate inference methods come in 2 flavors. Our first option is to simulate draws directly from the hyperparameter posterior distribution. MCMC methods can do this, but are generally quite expensive to run. The second option is to create an approximation to the hyperparameter posterior and then draw samples from the approximation. This is otherwise known as density approximation, of which there are many methods that have been used in the literature. I'll now discuss the 2 methods we investigate for this purpose, MCMC and Variational Inference. MCMC is a biased random walk that explores the target distribution, visiting locations proportional to their probability. Because we have access to the gradient of the hyperparameter posterior, we can use Hamiltonian Monte Carlo, also known as hybrid Monte Carlo. It uses the gradient information to simulate Hamiltonian dynamics and gives the random walk momentum. New locations are proposed by simulating a path of L steps, which results in L inversions of the n by n matrix per MCMC step, which is particularly costly. Thankfully, we don't have to tune the parameters of HMC itself because we make use of the NUT sampler, which does it for us. Here's an example of an MCMC run. It starts at the black dot and takes steps around the distribution of interest. As the run progresses, more and more samples are collected. Typically, we discard the initial samples because they may be far away from the target distribution. This is known as burn-in. Additionally, because sequential samples will likely be correlated with one another, we only take every k samples, which is known as thinning and results in decorrelated samples. Unlike MCMC, Variational Inference tries to find the most similar approximate density to a given target density, turning the inference problem into an optimization problem. It starts by first specifying a family of parameterizable densities that capture the features of interest of the target density. The idea behind this is to pick a family of distributions that are expressive enough to model the target density well, but simple enough to enable efficient optimization. It then tries to find the distribution Q star that minimizes the KL divergence to the target density. Unfortunately, this calculation is intractable, but thankfully, instead we can maximize the elbow. It is shown that this minimizes the KL divergence. In this work, we'll be focusing on two of the most popular approximations, the mean field and full field approximation. In the mean field case, we model each hyperparameter with an independent Gaussian. In the full rank case, we also include interactions between hyperparameters. To ensure the covariance of this Gaussian is always positive semi-definite, it is parameterized in terms of its Cholesky decomposition. Here we can see the bean-shaped distribution again, and the mean field approximation to it. It fails to capture the distribution stretch shape. The full rank approximation, on the other hand, has enough freedom to more closely fit the elongated shape. In summary, fully Bayesian optimization contains two main steps. First, we must draw samples from the hyperparameter posterior to obtain effectively M models, and then we must optimize the approximate integrated acquisition function by averaging the acquisition function evaluated on each of these models. Here we can see an example of a Bayesian optimization carried out using map estimates on the left and a fully Bayesian approach using MCMC samples on the right. Note to start with that the right-hand plot has more uncertainty compared with the map approximation. As we progress over time, the map estimates quickly get stuck in local optima and repeatedly sample close to the same location. On the other hand, the fully Bayesian approach lets it quickly escape the local optima and continues to sample in a slightly more exploratory manner. It quickly locates the global optimum. In the following experiments, we wish to look to establish whether using a fully Bayesian optimization approach actually improves the performance of Bayesian optimization compared to the standard approach of just doing map estimation. We compare map estimates to fully Bayesian optimization using Hamiltonian Monte Carlo, mean field variational inference, and full rank variational inference. We compare each method over 15 synthetic benchmark functions with different levels of noise, ranging from the noise-free case to 20% of the possible range of the function, with both isotropic and ARD kernels, and using the EI and UCB acquisition functions. Each combination of method, acquisition function, kernel type, test function, and noise level was repeated 51 times. This amounts to approximately 80 years of computation. Here we summarize all experiments carried out. Bar heights correspond to the number of times each inference method was the best performing or statistically equivalent to the best performing method according to a one-sided paired side rank test with Holm-Bonferroni correction. Each group of 4 bars corresponds to a different noise level, and each plot is for a different acquisition function and kernel combination. Starting with the upper left plot, we can see that the map approximation, in blue, is best when using EI with an isotropic kernel. The hyperparameter posterior is likely simple enough that given it only has 2 or 3 parameters, it quickly becomes sharply peaked, and thus a point estimate will suffice. On the other hand, in the top right plot, when we have more hyperparameters, that's in the ARD case, MCMC inference comes out on top. This is likely because the posterior distribution is higher dimensional and thus less likely to become dominated by one mode in the same amount of data. The bottom 2 plots show a different picture, that any sort of approximate inference is detrimental to UCB. Given that UCB is almost always too exploratory to start with, it is not wholly surprising that making it even more exploratory leads to worse performance. Because MCMC was generally superior to both variational methods, we compared using map estimates and performing MCMC inference at the test problem level. Each rectangle is coloured based on whether map or MCMC were best, blue or red respectively, or whether there were no statistical difference between the two methods, in which case it is coloured in white. Rows represent test problems with the dimensionality shown in brackets. Columns correspond to the noise levels, and groups of columns correspond to the combination of acquisition function and kernel type. In the left-hand group of columns, there's not much between map and MCMC using EI with an isotropic kernel. Particularly in the noise-free case, the far left column, all the rectangles are white except for one, indicating virtually no difference between the two. In the noise-free case, using EI with an ARD kernel, there's either no difference between the two methods, or MCMC is better out of 4 out of the 5 times. It's less clear which is better as the noise level increases. As can be seen from the large swathes of blue on the right-hand 2 columns, the fully Bayesian approach is almost always worse than map estimates for UCB. In order to investigate whether UCB and EI were really more exploratory when using approximate inference methods compared to map estimates, we calculated the Euclidean distance between consecutively evaluated locations for each optimization run. The distances shown have been normalized to reside in 0, 1. The idea here is that if there are large distances between consecutively evaluated locations, an acquisition function must be selecting locations that are far apart and thus was more exploratory. As we can see here for UCB, map estimates, which are the blue lines, tend to be lower than that of the other colours, indicating that the approximate inference schemes are increasing the amount of exploration. As we increase the noise level, this effect becomes more noticeable. For expected improvement, there is no consistent pattern of map always being less exploratory than the approximate inference schemes at the lower noise levels. Although as the noise level increases, the approximate inference schemes are sometimes lead EI to be more exploratory, and hence the blue lines start to get a bit lower. We now compare the combinations of acquisition function, kernel type, and inference scheme, map versus MCMC, for a given noise level in order to try and ascertain which combination of methods one should pick in general. In the noise-free case, the upper left plot, clearly EI using the ARD kernel and MCMC inference is the best. All on the top left plot, EI is much better than UCB. As the noise level increases, EI tends to have worse performance compared to the normal noise-free case, whereas UCB deteriorates less rapidly, resulting in UCB gaining in performance relative to EI. EI's deteriorating performance at higher noise levels may indicate that the surrogate model is poorer at representing the noisy function, leading to insufficient exploration. This is in contrast to the more exploratory UCB, which overexplores in the noise-free case. As a future piece of work, we'd like to investigate strategies to better mitigate this level of observation noise. So to conclude, in the noise-free case, a fully Bayesian approach is best when using EI, and in particular EI using an ARD kernel and MCMC inference outperforms all other combinations of methods evaluated. MCMC is generally superior to both the mean field and full-rank variational inference approaches. This indicates that the hyperparameter posterior is poorly represented by the Gaussian approximations, and that a more complicated approximation may be needed in the future. In the noisy case, it is less clear whether a fully Bayesian approach leads to improved performance. We think that this may be because the levels of additive noise we introduced were too large for the GP to cope with, and therefore led to modelling difficulties. However, even disregarding all of the results here, we'd like to argue that it's better to take into account as much of the uncertainty in the modelling process as possible. Performing a fully Bayesian approach with respect to the model's hyperparameters allows us to do this in a more principled way, even if it doesn't always improve performance over the map estimates. In future, we'd like to look at further ways to increase the performance and reliability of Bayesian optimization. One such direction to do that is to look at improving the modelling of difficult to model functions, such as those with discontinuities or non-stationarity, because often we don't consider if the function we're trying to optimize could even be represented by our choice of kernel prior. And with that, thank you very much.